So we now need to draw the line of best fit. To draw the line of best fit is a bit tricky. We must ensure that the line of best fit is fitting. Now for it to fit, it must leave an equal number of points below as it leaves above. So the idea is to be able to have a line that perfectly fits all the points. I think that this is the best position for the line of best fit, and I'll justify why, but I'll draw it as of now. First and foremost, I'll draw it. Now, this is the line of best fit that I drew. If you check my line of best fit, you can be able to see that this line of best fit you can be able to see that this line of best fit, I will do point by point. As you can see, the distance between this line of best fit and this point, the distance between the line of best fit and this point, the distance between the line of best fit and this point, these distances are approximately equal. If you check them out well, they are approximately equal, those line points. But however, we have these 2 points at the top, and only one at the bottom here. So I think that the balance is fair, considering that then we have another point at the bottom and another point at the bottom. I think that the balance is fair. The line is as close upwards as it is downwards. So let me remove all that so that we can continue. Okay, so now that we have drawn the line of best fit, we need to draw what is called the line of worst fit. The line of worst fit must start either from the bottom of one error bar and end as best as possible at the top of the error bar at the top. What I mean is that if I start from the bottom of this error bar, I must try by all means to end at the top of this error bar as much as I can. That's the line of worst fit, or the worst acceptable line. So to do that, I could start from the top of this one and try to end at the as bottom as I can with this one. So the idea is to try it and to see which one works for you. For example, if I start from the top here, it is obvious that the moment I start from the top of this error bar, the moment for it to go through the first error bar already, it's a false start. It cannot work that one. Well, now let me try to start from the bottom of that error bar. It can go. If I try very well, it can go through every error bar. It can go through every error bar like this. Now, before I set off for this one, which seems to be the best possible scenario, let me try starting from the bottommost here. So I think that the best line of worst fit has to be this one. It passes through every error bar. This is the best possible line of worst fit. It is near the line of best fit, of course, but we have nothing that we can do to save ourselves from there. And the good thing is that it crosses the other line. So that is the line of worst fit, my line of worst fit. And not only that, I'm going to label these 2 lines. I'm going to label the one that I called the line of worst fit. I'm going to label the one that I called the line of best fit, or the worst acceptable line. So this one is the worst acceptable line, whilst this one is the line of best fit, it is important that we label these lines to differentiate between the two. Now that I've done this stage, the next stage that follows requires for me to find, determine the gradient. As you shall see, it says determine the gradient of the line of best fit, include the absolute uncertainty in your answer. So, for this question, you need to find the gradient of both the line of best fit and the gradient of the line of worst fit. You need to find both gradients, the gradient of the line of best fit and the gradient of line of worst fit. You must find both of them. Now, to do that, you need to draw a triangle that will satisfy both. For me, I find that sometimes don't complicate things too much, but your triangle must cover more than half of the graph. So I'll use a ruler here so that I don't add too much, and there must be different values there. So I'll start from here, I'll start from there. Okay, let's see. I think I can go now horizontal, or I can go horizontal here. The ear seems to be fine. I can go horizontal here. So I go horizontal here. So let me conclude my line here. Okay, it's not very pretty there. Not very nice. Okay, so now that we have drawn our triangle, it's about finding the coordinates, and we have to find them quickly so that we don't waste time, and it will be wiser to label them. Personally, I prefer to label them as quickly as possible. So, for example, I will label my line of best fit and my coordinates here. For example, here, the coordinates are, of course, I didn't do it perfectly, but here the coordinates are 1.62 for the y value, and for the x value, it's not pretty, but it's 1.11. So the x value is 1.1. It's 0.11, sorry. And the y value it's a 1.62. Then I need to find the coordinates for this point here. The x value, it's already 0.11, and the y value, we can say that it's 1.64, I think. Okay, now next I have to find the coordinates here. Forgive that my line is not exactly where I wanted it to be. I wanted it to pass through this point, this coordinate there. Now I already know this coordinate as my first coordinate. This coordinate as my first coordinate was the x value being 0.018, and the y value being 0.8. Okay, now finally I'm left with this coordinate here. The x value, we could say that it's 0. We can say that it's 0.014, and the x value is, the y value is 0.8. Now that we have these coordinates, we can find the gradient. I want to find the gradient of the line of best fit and the line of worst fit. And when you find those gradients, then what we do is that we find this gradient first, and then we of the line of best fit and the line of worst fit, then we subtract them to find the uncertainty in the gradient. So that is our next stage. To do that one now, we need to bring the coordinates. Remember the line of best fit, which one it is, and the line of worst fit, which one it is. So I'll start here. My gradient of the line of best fit, I'll write it gradient B. That's for my line of best fit. I'll say y2 minus y1 over x2 minus x1. Then I'll go back at once to find the value of y2 and the value of y1. So for the line of best fit, my line of y2 was 1.64 and my value of y1 is 0.8. Yeah, 0.8, 1.64 and 0.8. So I'll go back here. 1.64 minus 0.8 divided by the other coordinate is 0. It's actually the other coordinate is the x values, and as it is the x value, it's 0.11 minus 0.018. Okay, so to find the gradient there, but remember that the gradient must also always be considered that what are the units for the y-axis, what are the units for the x-axis. Remember the y-axis is times 10 to the power of minus 3, so we must always remember this when we write our answers there. So I will do it by calculator. This is 1.64 minus 0.8 divided by 0.11 minus 0.018, close bracket there, we get 9.13 times 10 to the power of minus 3 on account of that y-axis labeling. Now we have to find the gradient of the line of west fit now. Gradient of the line of west fit, this one now again y2 minus y1 to give us over x2 minus x1. This gives us 1.62 minus 0.8, if you remember very well, over 0.11 minus, let me check the value of the line of west fit, the other coordinate. It's 0.014 minus 0.014, 0.014. So having found these two values now, we subtract them to find the uncertainty in the gradient. So we now say 9.13 minus 8.54. That gives you, so when we find the uncertainty in the gradient, as I said, uncertainty in the gradient, we are going to then say 9.13 minus 8.54, that will give us 0.59. So ultimately we can visually say that our answer is the gradient, actual gradient of the line of best fit, plus or minus, I'm putting it in brackets there, 0.59. I'm leaving my uncertainty to two significant figures, but usually we should leave it to one significant figure, but two can leave. So we have written our gradient. There is our gradient with this uncertainty. Then next stage now. Next stage says, determine the y-intercept of the line of best fit. Include the absolute uncertainty in your answer. So we are being asked to find the y-intercept of the line of best fit. Now to find the y-intercept of the line of best fit, all the terms, we should use the equation of a straight line. The equation of a straight line says y is equals to mx plus c. So we want to find c. So c is equals to y minus mx. We now have m. M is the gradient. We now have m. M is the gradient. So what we need now is to find the c. So how are we going to find c? We will substitute. Now, remember the question also asked about the absolute uncertainty in your answer. So actually, we are supposed to find two values of y-intercept. Now, what is the difference between these two values of y-intercept? Now, I'm going to use y1 and x1 here. What are the two differences in values of c? They will be found using the two different gradients, the gradient of the line of worst fit and the gradient of the line of best fit. So that's the major difference between the two y-intercepts. When we subtract them, we would have found the uncertainty in the y-intercept. So y1, I'm going to go back here and say, whom did I take as my y1 for the gradient of the line of best fit? My y1 was 0.8, my x1 was 0.018. So I'll come here and I'll say 0.8 here minus the gradient, which was 9.13 times 10 to the power of minus 3 times 0.018. This will give us the first uncertainty of the line of worst fit now, of best fit, sorry. So this is 0.8 minus 9.13 times 10 to the power of minus 3 times 0.018, which gives us, so this gives us 0.79999, which is actually 0.8. So in real sense, it is saying that our y-intercept is 0.8, which doesn't make sense much if you consider it well. Okay, the reason why it doesn't make sense much is because I did not account for the fact that the 0.8 here was also times 10 to the power of minus 3. So when you recalculate it, it's 0.8 times 10 to the power of minus 3 minus 9.13 times 10 to the power of minus 3 times 0.018. This now gives you a proper y-intercept, which is 6.36 times 10 to the power of minus 4. That's our y-intercept. Now, having found this y-intercept, then we go for the value of C, the second y-intercept for the line of best fit. This was y-intercept for the line of best fit. Again, we repeat the same thing, but the difference is that for the line of worst fit, we use the value of y1 and the value of x1 and also the gradient for the line of worst fit. And so what we do, we come here, the value of y1 was 0.8, the value of x1 was 0.014, the gradient was 8.54 times 10 to the power of minus 3. So we come here, we say 0.8 times 10 to the power of minus 3 minus 8.54 times 10 to the power of minus 3 times 0.014. So then we calculate this one, 0.8 times 10 to the power of minus 3 minus 8.54 times 10 to the power of minus 3 times 0.014. This will give us 6.80 times 10 to the power of minus 4. So we subtract these values without care for which one is the bigger of the two. So subtracting them, will give us an uncertainty. So the absolute uncertainty in the y-intercept delta C will be, as we can see here, 6.8 times 10 to the power of minus 4 minus 6.36 times 10 to the power of minus 4, which gives us 4.4 times 10 to the power of minus 5. So that's our uncertainty there. So now we have the absolute uncertainty in the y-intercept. We have the y-intercept also, the y-intercept of the line of best fit. So now what we write 6. I would prefer to write it 6 point. Yeah, all right. I prefer to write it as 63.6 times 10 to the power of minus 5. Okay, so before I put minus 5 there, let me join it with the uncertainty. The uncertainty will be 4, then both of them in brackets together. Again, 4.4, both of them in brackets, times 10 to the power of minus 5. So that's the y-intercept and its uncertainty. So now the question then comes and says, using your answers to A, C3 and C4, determine the values of A and the value of Q. Include an appropriate unit. So the answer in A, remember, was for the gradient, was the expression for the gradient and the expression for the y-intercept. You are being asked, using the expression for the gradient and the expression for the y-intercept, you're being asked to find, and here, I must correct this part here, I forgot to put A here. You're being asked to find the value of A and the value of Q. So I think that the value of Q is much easier to find. We will just take the gradient and we equate it to this one. And we equate it to that expression. The value of Q, I think, is much easier to find. So we are saying 4 pi permittivity of free space over Q is equal to the gradient that we found. And we find the gradient of the line of best fit is 9.13 times 10 to the power of minus 3. That way it will be in the proper units. So in which case, now we need to find who is Q in this case. So we have to make Q-subject formula. So we'll then say Q is equals to 4 pi times 8.85 times 10 to the power of minus 12 divided by 9.13 times 10 to the power of minus 3, like that. So this will give us a value of Q. And the value of Q that we get here is approximately, let me punch into the calculator. This is approximately 4 times pi times 8.85 times 10 to the power of minus 12 divided by the gradient is 9.13 times 10 to the power of minus 3. So this gives us a value of Q, which is 1.22 times 10 to the power of minus 8. For now, that is fine. Now we need to find the value of A. The value of A, I believe we can appreciate that the value of A was the expression for the y-intercept. The expression for the y-intercept was 4 pi permittivity of free space A over Q. So this one's equal to the y-intercept, but we now know that the y-intercept is 63.6 times 10 to the power of minus 5. So now we want to find for Q now. So for Q, we then say Q is equals to 4 pi. The permittivity is 8.85 times 10 to the power of minus 12. And remember, we are looking for the value of, A. So let me actually erase. We're looking for the value of A. So to find the value of A, we're going to make substitute formula there. So we're saying A is equals to 63.6 times 10 to the power of minus 5 multiplied by the value of Q that we just find, which is 1.218 times 10 to the power of minus 8 over 4 pi permittivity of free space, like that. So I'll punch this in. That would be times, okay. We divide by the denominator, which is 4 times pi times 8.85 times 10 to the power of minus 12. This gives us a value of A, which is 0.0696, which ultimately is 0.07. We can live with it like that. So we found the value of A, which is 0.07. We have found the value of Q, which is 1.22 times 10 to the power of minus 8. Okay, so now we need to find the unit, and to find the unit well. And also, it is proper also for us to leave this answer to 2 significant figures. There is no answer in physics that you can ever be less than 2 significant figures, except for uncertainty. But considering that we used the values which were to 2 or to 3 significant figures to find the value of A, we are supposed to leave it as 0.070. And the value of the other one is 1.22 times 10 to the power of minus 8. Try by all means to leave all your answers to either 2 or 3 significant figures, the calculated values. For uncertainty, try by all means to leave it to 1 significant figure if you can, unless if it is impossible, then you leave it to 3 significant figures. So in this case now, we are going to leave our answer. Now we need to put the unit now, because they wanted us to find the unit for Q. So the question is, how do you find the unit of Q? The unit of Q, the good thing is that we know the unit of permittivity. So the gradient of the graph, if you check the gradient of the graph well, we had a column where it was 1 over V. So it was the y-axis, which means that the unit was approximately V to the power of minus 1. That was the y-axis. Then the x-axis was in meters. So the gradient was per volt per meter, if you have to consider it well. Then, so that's the units of the gradient. But in this equation for Q, we want to find the units of Q. So Q is equals to, in this case, let's say Q is equals to 4 pi permittivity over gradient. So the units of 4 and pi, they don't have units. So the units that matter are the units of permittivity of free space, which is F farads per meter. So over the units of gradient, which is per volt per meter. So because this is similar, this and this cancels. So in that regard, that volt rises to become Fv, as you can see. Now, this of course was, but it could be a waste of time considering that Q wasn't actually been said. What was Q actually from the word go? Q was said to be the charge on the sphere. So sometimes instead of struggling like that, you just write Coulomb. It would have been, sometimes we don't know, of course, it could have been microcoulomb, considering the power of 10. But you wouldn't be too wrong. But because here I made sure that the power of 10 were corrected for, ever since I calculated the gradient, and then this is correct like that. Finally, the question is asking us to look for the percentage uncertainty in A. Now, to look for A, we have to be clear how would we look for A. We said for pi permittivity A over Q was equal to y intercept. So if we are to find the uncertainty of A, we usually ignore everything else which is a constant. So let us say that it will be A is equals to Q times Y, let me just say times C, so that we don't confuse each other, times the y-intercept, which is C. So how then do we find the uncertainty here if it is like this? We need to deal with finding, because we're looking for the percentage uncertainty of A. So we need to find since there's multiplication, the law of multiplication, we must find the fractional uncertainty of A over A, which is equal to the fractional uncertainty of Q over Q plus the fractional uncertainty of C over C. Ultimately, fractional uncertainty of A multiplied by 100% will give us the percentage uncertainty. So the first things first, we must find the fractional uncertainty in Q. But the problem is, how then do we find the fractional uncertainty in Q? How did we find Q? Q was a simple case of 4 pi permittivity over Q was equal to gradient. So let me use M there. So in which case, Q was equal to 4 pi permittivity of free space over M. Now, this was using the division rule, but however, the fact is to remain that the numerator was a constant, and when we are considering fractional uncertainties, constants, we ignore them. So in this case, this would become delta M over M. Sorry, delta Q over Q is equals to, the numerator is a constant, so this uncertainty is 0, fractional uncertainty is 0, but the denominator is fractional uncertainty is delta M over M. So in other words, delta Q over Q is delta M over M. So in which case, it's delta M over M plus delta C over C. So in other words, it's the fractional uncertainty of A is the fractional uncertainty of the gradient plus the fractional uncertainty of the y-intercept. So deltas, we have these uncertainties anyway. So we go back to the gradient. The gradient, we are going to say 0.59 divided by 9.143 for gradient. So let me write that down if I forget. So it's 0.59 divided by 9.13 plus, for y-intercept, is 4.4 divided by 63.6. Remember, why I'm ignoring the power of 10? It's not necessary, since it will cancel out 63.6 here. Okay, so let me do that one. So it's 0.59 divided by 9.13 plus 4.4 divided by 63.6. This will give us 0.1338. So ultimately, in terms of percentage, that's just 13% after multiplying the rand by 100. So it's 13%. So the percentage in renting A is 13%, and the paper is